Hello everyone and welcome to TLE Eliminators PCD for weekly contest 471. Today we'll be discussing all the problems from A to D. So let's get started. First problem, sum of elements with frequency divisible by k. Okay, you're given an integer array nums and an integer k. Return an integer denoting the sum of all numbers whose frequency is divisible by k or 0 if there are no such elements. Note that an element is included in the sum exactly as many times as it appears in the array, right? So we don't need to include an element once if its frequency is divisible by k, but every element whose frequency is divisible by k should be included. And the frequency of an element is the number of times it occurs in the array, right? So we all know that. Okay, so given input is like, for example, 1, 2, 2, 3, 3, 3, 3, 4. K is equal to 2. So that means that frequency is divisible by 2, or maybe basically even frequencies should be taken. So basically 2 has even frequency and 3 has even frequency, right? The other two are only appearing once, so they have odd frequency. So then we sum up these numbers. So this will be 12 plus 4 and we get 16, right? So that's the answer. And they have given the similar explanation for this example. Okay, n goes up to 100. So big of n squared, n cubed, everything works. Each number goes up to 100. So that also is there. And k goes up to 100. Okay. So how do we solve this problem? Well, this is a straightforward implementation question. I think there's nothing much to it here, but we can just write it as we can say make a frequency table. Okay, so it can be a map, it can be a unordered map, it can be a array also because there's only 100 possible numbers. But yeah, first step one, make a frequency table of all elements, right? Make a frequency table for all elements. And then step two, go through all elements once again, right? Set sum equals 0, then go through all elements, go through all elements. If in our frequency table, so frequency of this element x is divisible by k, right? If it's divisible by k, then we can add this element x to the sum, right? So this is the step 2. For everything which has divisible by k frequency, we add that to the sum. And then step 3, simply return the sum, right? Return the sum. So all these steps are pretty basic. So if you know basic programming, I'm pretty sure you would know how to make a frequency table, right? You can use map or array or unordered map, hash map, whatever you want to call it, unordered map, anything you wish, right? And then you can return the sum. In fact, it's perfectly fine to do an n squared solution where for each element you count its frequency because n only goes up to 100. But then the time complexity of this solution, which I have given to make the frequency map, is big O of n log n if you use map, if using maps, and big O of n if using unordered map or vectors or arrays. Unordered map or array, right? So that's the type complexity of this code. Let's have a look at what one implementation of this would look like. So I implemented C++, as you all know. So sum divisible by k. The vector numbers and the integer k are our input. We make a frequency map. So for each element in this vector, we increment by 1 the map value of that vector. So basically we're counting its frequency. Now we want to find our answer. So we'll make sum equals 0. Again, for each number, if the map value is divisible by k, we can add that to the sum. And then in the end, we return the sum. So that's about it for the first question. Pretty straightforward, I think. Big O of n also, we can solve this in. But yeah, I used maps because they're convenient. That's it. Okay, let's move on to the next question now. Okay, the next question is longest balanced substring 1. You're given a string s consisting of lowercase English letters. A substring of s is called balanced if all distinct characters in the substring appear the same number of times. Return the length of the longest balanced substring of s. A substring is a continuous non-empty sequence of characters, so obviously you know that. So basically we just need to check if all the distinct characters appearing in a substring appear the same number of times, and we need to find the longest such one, right? Now pay attention to the constraints. The constraints say that the length is less than equal to 1000, right? The length is less than equal to 1000, so that does help us a lot, right? So problem B, um, let's summarize the problem. So the problem says find max length substring uh, such that all distinct characters have equal frequency, right? Have equal frequency. Okay, so how do we do this? We're given that the length, which I'm going to call n of the string, is less than equal to 1000, right? And because n is less than equal to 1000, we can make one obvious, like we can know that the expected type complexity can be big O of n squared. Okay, big O of n squared. Why so? Because uh, if you have 1000, n is 1000, then n squared will be like 10 to the power 6, right? A millionish. So obviously we can do a millionish operations in a second. So yeah, we can definitely do n squared solutions for this. So if we have allowed n squared solutions, then that means that we are allowed to iterate over all possible substrings. Okay, we are allowed to iterate over all possible substrings, right? Because all possible substrings are also n square itself, right? Each substring has a L pointer and an R pointer, correct? So given a string, so it's a very basic brute force type of question where you need to know how to do a brute force over all possible substrings, right? So you have an L and you have an R pointer, and as you increment your R pointer, basically that makes you a new substring, right? So as you increment R plus plus, you get a new substring. Once you have done all these R, then you can increment your L, and then you can move your R pointer again, right? So that's how you find all the possible substrings, right? So this gives us a very straightforward solution again. So it's pretty straightforward brute force question. Since we have the time complexity for it, type complexity for it, we can just iterate through all possible substring, through all possible substring, right? And first we need to check if it satisfies the condition, right? So we need to keep track if equal frequencies of all elements, right? And if that's true, if true, then we can see whichever is the maximum size, right? Then find the max sized one, right? So this is mostly brute force and implementation, right? There's nothing much to think about this problem. So let me just write pseudocode directly, right? Let me just go write the pseudocode, right? Pseudocode. So basically it's going to be something like this. For uh, L is your left pointer, right? So for L goes from 0 to n minus 1, right? And we can just make the brackets, and then for R goes from L plus 1, right? So the right pointer must always be from L plus 1 to n, right? So now in this R to L, we need to find the counts of the characters. We need to know whether they're distinct or not, right? But if we find the count over here, it will become big O of n cubed, right? We cannot go through L to R again, because now it will become big O of n cubed, right? So what we need to do is basically we need to start going through it here itself, right? We need to start adding the distinct characters at this point itself. So what we can do is basically, like as we increment the second loop, we should also be keeping track of the distinct characters. Okay, so we can basically make a frequency map. You can make a map, but if you use a map, it'll be log n, right? And because the constraints are dset, it's preferred not to use a map. Since there are only 26 characters in the English language, you can just use a normal vector, right? So we'll make a frequency vector, vector of size 26, right? So why size 26? Because 26 characters in the English language. We can say frequency of L plus plus, right? And now we're going to move the right pointer. So for R is equal to L plus 1, R is less than N, R plus plus, right? I'm moving the right pointer. Now what we can do is we can say frequency of R plus plus, right? Frequency of R plus plus. Now we can do the checking step. So now check if, what are we going to check? We're going to check if all the values which appeared. So we're going to check the frequency map. All values are same. What if something did not even appear? Then it will have frequency 0, right? So all values are same or 0, right? So if there's 0 values, we just ignore them, but the remaining values should be the same, right? And we can check this in big O of 26, since there's only 26 characters, so it's constant time itself, right? And then if this is true, update the maximum length, right? Update the maximum length, right? Which we found so far. Obviously the length will be R minus L plus 1, right? So in the length between L and R range is R minus L plus 1, right? And then once both of these loops are done, we can simply return the maximum length, right? Return the maximum length. The time complexity for this will be big O of n squared, or if you want to be precise, it will be big O of 26 times n squared, where this 26 is number of letters in the alphabet. Because that's what the vector we're making, right? And we're checking that vector. Okay, so pretty straightforward brute force problem. Let's have a look at the code. Okay, so here's the code for the problem, and basically almost exactly what I told you here. N is the size of the string. Answer is equal to 1, because obviously one character itself will form a balanced substring. I goes from 0 to n. Here I'm making my frequency map, which I'm calling count, and then the current character I increase in my count, right? Count of s of I plus plus. Now for each j which goes from I plus 1 till n, count of that j also plus plus. Now I'm going to check if all the characters which are greater than 0 frequency, I have the same count as the first character, right? So we just want to make sure they're all equal. So I'm just checking if they have the same count as the first character. So that's what we do. We go through all the possible frequencies and we check if at any point the count becomes different from the first character, in which case we can set valid as false. And if it's valid in the end, we just update the maximum and we can return that, right? So pretty straightforward. Today's contest was pretty simple, I think. Not very tricky questions, mostly straightforward questions. So yeah, that's about it for this question. Moving on, let's go to the next question now. Problem C. So before we get started with problem C, I'd like to tell you about TLE Eliminators flagship courses. Our flagship courses are out right now, which have 4 different levels for people who are trying to learn or get into competitive programming. The first level is for complete beginners who are just starting their coding journey, and it goes all the way up to level 4 for coders who can solve up to 3 problems in most div2s. So yeah, they're at super affordable prices, and each level includes more than 40 hours of recorded lectures, more than 100 plus practice problems, and hints and video solutions for all of them, so that if you ever get stuck, you have progressive hints which get like a small hint and a slightly harder hint and so on, as well as doubt support. So if you're completely stuck or you're stuck in some other problem and you need help, then high rated coders are there available almost 24/7 to help you and clear your doubts. So you just create a doubt and within 10 minutes someone picks it up and explains it to you. So yeah, go check out the course. based on what current level you are and what topics you need to practice, you can see which level is right for you. You can also check out Priyansh's video on what level is right for you. All right, so moving back to the problems. Problem C. It's a continuation of this problem, longest balanced substring 2. So in this problem, your string S is containing only the letters A, B, and C, and the rest of the problem is pretty similar. We just need to find the length of the longest balanced substring, which is balanced if all the distinct characters occurring have the same frequency, right? And also, the length has become 10 to the power 5, right? So there have been two changes. We can't do brute force anymore because now the length is 10 to the power 5, and the string S only has the characters A, B, and C. So let's note this down, right? So the expected time complexity now will be big O of n or n log n, right? Because length is now 10 power 5. And one more thing we need to note down is string has only a, let me just write that properly, A, B, or C characters, right? Okay, so how do we approach this? And the way we approach this problem is by dividing it into a few cases. Okay, so if you want to find, let's assume that the string only has two characters. Okay, you just imagine that the C we are ignoring for now, and it only has A and B. Okay, it only has A and B. And how do we find the longest balanced string, right? Longest string where the frequency of A and B are the same. So let's simplify the problem to get intuition, right? So intuition finding. So let's try to simplify the problem. We're going to chase some intuition. Simplify. Imagine there were only two characters. Okay, imagine only two characters, right? Then what you could say is basically one algorithmic approach to solve the question of what is the longest string when you have only two characters is the following. Okay, we're going to use the approach of balance, right? So direct balance, what we're going to do is we're going to say that each of the A's represent a +1. Okay, so each of the A will represent a +1, right? This represents the +1, +1, +1, right? And each of the B's will represent a -1. Okay, so each of the B's will represent a -1, right? So, and what basically happens is if you have a sum of 0 at some point, right? If you have a sum of 0 at some point, like for example, we have this thing, this whole range, right? It has a sum of 0, right? Sum of this range is 0. So we can say that it's balanced because the A's and B's have cancelled out, right? We can say that this is balanced because the sum is 0. So now how do we find sub arrays or substrings which have a sum of 0? What we can do is basically keep track of the prefix sums. Okay, so we are going to use the topic of prefix sums, right? So if we have that, basically what we want to say is in some L and R, right? Like for example, in this L and this R, right, they sum to 0, this sums to 0, right? So basically we can write it in prefix sum format as like this. We can write a formula. We can say prefix of R minus prefix of L minus 1, correct? Prefix of R minus prefix of L minus 1 is equal to 0, right? So we get this formula, correct? And now let's rearrange this formula. Okay, so this is a very standard rearrangement. I think many people would already know this. So rearrange this formula and we get prefix of R is equal to prefix of L minus 1, correct? So every time, let's just double star this because it's very important. If this is your first time seeing it, please pay much attention go in depth and understand this, because this kind of idea is used a lot, right? So basically what we're doing is we're saying this is the prefix sum equation for that, and then when we rearrange it, we basically get prefix of r equals prefix of l minus 1. And what this means is basically at any 2 points, let me just write a summary of what this means. Summary of what this equation means is that if at any 2 points, r and l minus 1, okay, the prefix is same, the prefix sum value is same, then the range L to R substring is balanced, right? Is balanced, correct? So basically for every value of prefix sum, we just want to find the earliest value. So basically for every value of for every prefix of I, we want to find the earliest point. We want to find the earliest occurrence of equal value of, let's say, prefix of j of equal value, then from j plus 1 to I, it is a balanced substring, right? It is a balanced substring, correct? And one more thing to note is that we can write it like, so what is the length? The length will be equal to basically I minus j, right? I minus j, correct? So we can use a map for this. What we can do is we can basically use a map for this. Use a map, which will be like map of prefix sum to first occurrence, right? So for every prefix sum, we're going to store its first occurrence in the map, okay? So that's what our map will be. And then for every prefix sum, we can find the first occurrence of that prefix sum, and we can do length equals I minus j, and then we can check what is the longest one of these, okay? So the pseudocode for this will be, so this is only for 2 characters, only for 2 characters, right? So far we're only discussing 2 characters because we're doing +1 and -1 right now, right? So what we can say is basically we're doing for each so first we'll have prefix, like the balance will be equal to 0, right? So prefix equals 0, and also we need to have, like, if we start at the first character, that before the first character, that also counts as a valid one, right? So we need to add that as a map as well. So we can say map of basically 0, right? So the prefix of before the first character is 0 is equal to -1, right? The first occurrence of 0, first occurrence of prefix sum of 0, prefix sum of 0 occurs at position -1. Okay, that's what this means, at position -1. So before any characters are there, the prefix sum is equal to 0. That's what we're saying. Now for each character x, we can say if x is equal to a, then we can do x plus plus, else we can do x minus minus, right? Because equal to b now. And what we can say is we can update the map, right? So map of so basically we can say that if this prefix, okay, sorry, we can update prefix dot x, so prefix plus plus and prefix minus minus, right? So if map of prefix is not set, right, we want the first occurrence, so if it's not set, we will set the first occurrence of this prefix to I, okay, I, which is equal to which iteration we are on, right? So that's the first occurrence. Now answer will be equal to the max of answer and I minus map of prefix, okay? So I minus j, right? And j is equal to map of prefix. So that's what we're doing here, right? And then this gives us the answer for 2 characters, okay? So how do we move on to 3 characters? Checking balanced. So for that, we need to just use this idea with some casework. Okay, so we're going to use this idea with some casework, and what we can say is, for balanced substrings with three possible characters, okay, so there are many cases which happen. Okay, so one case which can happen is, we have something like a b c b c a. Okay, then the whole like this thing is balanced, right? This thing is balanced, correct, and this is of length 6. Another case which can happen is, for example, we have a b c, right, something like this. And now here the answer would be 4. The answer would be 4 because this whole thing is balanced, right? So it only consists of single character, so obviously it will be balanced, correct? And now there's another case which is like a b c b c b c, right? Now we can say this thing is also balanced because all the frequency of b and c are equal, right? Frequency of b is equal to frequency of c. So we have these three possible cases. What is that? The first case is basically balance requires string to have substring to have a and b and c, and f of a equal to f of b equal to f of c. Okay, now the second case is that balance is of only one character, is in a substring with only one character, so it can be a or b or c, right? A or b or c, and we don't care about frequency. Because it's already balanced, right? So we don't care about frequency, it's only one character, we don't need to compare the frequency. Third case is balance is in a substring with two distinct character, which will be basically AB, or you could say AC, or you could say BC, right? And we need f of the first character, so f of A is equal to f of B. That's the condition for this, right? So we need to check all three cases, right? So first case we need to check, second case we need to check, third case we need to check. This case is pretty simple. We just need to see if how many times a given character repeats, right? So pretty simple. Just check which character repeats the longest, right? So which character repeats the longest. Case 3 is also pretty simple, which is the same thing which we did right now. Basically we do +1 for the first character and -1 for the second character. +1 for the first character, -1 for the second character. And if you see the third character, you can just reset. Okay, if you see the third character, we'll reset the map. Okay, reset the map. Why are we resetting the map? It's simple, because when we see the third character, we cannot use that as a prefix anymore, right? Because the string has to only consist of the first two characters. So we can set prefix equals 0 and we can reset the map. Right. Now what if the balance substring is of the first type? It needs it has all the characters A, B and C, and we need frequency of A equals frequency of B equals frequency of C. Well, that also can be solved with our original idea itself, right? We need to have frequency of A equals frequency of B equals frequency of C. And for this, what we can do is, instead of having just one value for +1, -1, we can have a pair. Okay, we can have a pair, value 1, value 2, right? And this will store the values of A count minus B count, right? And this will store the value of C count minus B count. Okay, so that's what it's going to store. Basically, it's saying that we're going to do the +1 -1 thing itself, but in one case we're going to ignore the C's, and A's will become +1, B will become -1, C will become 0, and then B will become -1, C will be 0, A will be +1, right? And in the other value, A will be 0, B will be -1 again, C will be +1, B will be -1, C will be +1, A will be 0, correct? So basically what we're saying is the first two will check whether the B count is equal to A count, right? The first two are going to check if A count is equal to B count, the first value, and the second value is going to check if the C count is equal to B count, right? So that's what we're doing. Basically, we're saying that first we're checking for A count equals B count, and second we're checking for C count equals B count. Okay, that's why we have two values. And then we can do the same map trick again. We can say map of, instead of normal map of int to int, it will be map of pair to int, right? It's a map of a pair to int, and basically we're checking so for each character x, if x is equal to A, right? If x is equal to A, then value 1 plus plus. If x is equal to C, value 2 plus plus. If x is equal to B, value 1 minus minus, value 2 also minus minus, right? So this way we're maintaining the first prefix and the second prefix, and we're just going to check if this prefix occurred earlier, right? So we're going to check the value of map of value 1 value 2, right? So map of v1 v2, right? And we're going to put the earliest frequency of this map in here. So we can say that if map of v1 v2 not set, then we can say that map of v1 v2 is I, right? Is I equal to I, and we can say that answer is equal to maximum of answer and I minus map of v1 v2. Basically we need to know when this v1 v2 occurred in the start or the first time, and we can take that one's length, right, from I to this length. It's the same prefix sum logic again. Basically what we're saying is if we want the A count and B count to be equal, we're using the first value, and if we want the C count and B count to be equal, we're using the second value. All right, so that's about it. Let's have a look at the code, so then it'll be a bit cleared up. Okay, so n is the size of the string. Answer is initially 1 because obviously a substring of size 1 will be balanced. v1 and v2. So first we're doing this case. Okay, we're making a map from parent int to int. Map of 0 0 is -1. So for the same reason, before we have started the string itself, the prefix 0 0 should have a value of -1. For each character, if it's A, only v1 will change, v1 plus plus. If it's C, v2 plus plus. Otherwise it's B and v1 minus minus, v2 minus minus. And we can say that if this value is not a map, we set it, update the answer, correct? Now for all these three combinations, AB, AC, BC, right? Only these two characters are going to form our balanced string. So for those combinations we're checking, and X and Y are the two characters, right? So X equals the first character and Y equals the second character. Now here we don't need v1 v2, we just need V, right, which is our prefix value. So V equals 0. We make a new map, like the same kind of map. It will have the value to the first occurrence of the value, or the prefix to the first occurrence of the prefix. The map of 0 is equal to -1, right, as before. Now for each character, if the character is equal to X, value plus plus. If it's equal to Y, value minus minus. If it's equal to none of them, then we can clear the map and we can set value as 0 again, right? Why are we doing this? Because we want to reset it if we see the other character. Yeah, if the value was not there in the map, we put the occurrence of the first occurrence, and we also update the answer with I minus the first occurrence, right? So this will give us the length of the longest occurrence at I. Okay, now this is the final case, the case of only one character. So if s of I is equal to s of I minus 1, count plus plus, else count equals 1, and we take max of answer and count. So we have checked all three cases. This is the case of having three distinct characters. This is the cases of having two distinct characters, and this is the case of having one distinct character. Once you're done with all of these, you can just simply return the answer. And the time complexity if you use maps is big O of n log n. If you use unordered map, or if you use if you use unordered map, it will be big O of n, right? So time complexity, I'll just put it down as n log n, because you know that much optimization also is not that useful. But yeah, you can use unordered map if you wish, although the constraints definitely allow n log n solution, right? Okay, so let's move on to the final problem. Problem D. Problem D. Okay, so this problem, I feel for a tree problem, it's pretty simple in my opinion. Like usually a lot of times tree problems can be harder, but this felt like a slightly simpler side tree problem. So, but yeah, you need some number theory knowledge to be able to solve it. Anyways, you are given an integer n and an undirected tree rooted at node 0 with n nodes numbered from 0 to n minus 1. Is represented by a 2D array edges of length n minus 1, where edges of I indicates an undirected edge between the nodes ui and vi. You're also given an integer array nums, where nums of I is the positive integer assigned to node I. Okay. So each node has some number assigned to it, and there are also some edges in the tree, so which are given in our array edges. Okay, so normal tree question. Okay, so now we have to define a value t of I as the number of ancestors of node I such that the product is a perfect square. Okay, so we need to find the number of ancestors of every node such that the product of nums of I times nums of ancestor is a perfect square. Now we need to return the sum of all ti values for all nodes I in the range 1 to n minus 1. Okay, so yeah, they have defined ancestors, they have defined perfect square. Okay, so how do we approach this problem? Let's just see the constraints first. So n goes up to 10 power 5, and normal constraints nums goes up to 10 power 5. So nums is not that big, right? Keep that in mind. Yeah, so let's note it down. Okay, so let's try to visualize the problem. Okay, so basically it says we have a kind of tree, right? We have a tree which is something like this. Okay, and for every node, let's say for this node, we need to find all of its ancestors, which are, if you multiply its number with the ancestor number, it will form a perfect square. Okay, so let's say this one has a value of 27. Okay, here the node has a value of 27. Here the node has a value of of 10, let's say, and here the node has a value of 3. Okay, and what does the node have a value of here? Here it has a value of, let's say, 12. Okay, so now with which numbers will it form perfect square, right? So 12 into 3 is 36. 12 into 3 is 36, which is equal to 6 squared, correct? And also 12 into 27 is equal to 4 times 9 times 9, right? So as you can see, that is that's 2 times 3 times 3 squared, correct? So basically we can say that that's equal to a perfect square, correct? So here it forms a perfect square. Now what about 10? 12 into 10 is equal to 120, which is not a perfect square, correct? Because the factor of 5 appears exactly once. So basically what we need to do is we need to so the number of ancestors here will be 2, and we need to do this for all the nodes, and we need to find the sum of that. Correct? Okay. So here there are two simple observations which will give us the solution. And the first observation is a number theory based observation. So you need a some number theory, right? Some number theory. And basically, what does a perfect square mean? Okay, what is a perfect square? Perfect square. And what we can say is basically a perfect square is any number such that all of its prime factors, okay? So let's write the number n. So all of its prime factors is equal to some even number, like some even power, right? So p1 n1, p2 n2, p3 n3, so on, pn n okay, let's call it pm instead. So pm and m, right? So this is the where we're representing it as a product of prime numbers. And when you represent a number as a product of prime numbers, if all of these primes have even exponent, right, even, they appear even number of times, then it is a perfect square. Okay, then it is a perfect square, right? So basically for each number, correct, so for each number, let's just take a node u and its ancestor, which is the node v. Okay, so this one has some number n, and this one has some number n2. Okay, n1 and n2. This is the node and this is its ancestor. How do I know if the product is a perfect square, right? How do I know that the product is a perfect square? Well, one way I can do is obviously multiply them, but I don't have the time complexity for that. But what I can say is, if this one has any odd ones, right? If this one has some prime decomposition, like it's p1 squared, p2 cubed, p4 to the power 4, p5, something like this to the power 1. Okay, so this is the prime decomposition. Then the ones which are squared are fine, right? The ones which are squared are fine. We can ignore them. The ones which are power of 2, power of 4, well, the ones which have even power, we can ignore them. But the ones which have odd power, those are the prime numbers we care about. Okay, so we can have this value which is equal to p2 times p5, right? And as long as you multiply it with p2 times p5, then this value will become even, and this value will also become even, right? We want these values to be even. So as long as you multiply it with some number that also has an odd value of p2 and odd value of p5, then they will form a perfect square. Okay, similarly in n2 as well, if we have some p7 to the power 2, p9 to the power 10, and as long as we get p2 times, let's say, p5 to the power some odd number, right? This is some odd number, this is some odd number, then we can multiply these two numbers and we can have the perfect square. Okay, so let me just give you an example of what I mean. So let's just take an example. The numbers like 12 and 27, they multiplied to form a perfect square, right? So 12 is equal to 2 into 2 into 3, right? So that's equal to 2 squared into 3 times 1. 27 is equal to 3 into 3 into 3, right? That's equal to 3 to the power 3, right? So now if you want to find the ones which are odd, right, the factors, the prime factors which have odd exponent, over here it's 3, right? It's 3, and over here also it's 3, correct? So since the same prime factor have odd exponent, if we multiply them together, we'll get 2 squared times 3 times 3 times 3 squared, right? So this is equal to 3 squared times 3, right? So basically these two will form a perfect square. These two are going to form a perfect square, and that's pretty much what we want. So basically let's summarize what we noticed. Let's define a new thing. Okay, let's define a stripped version of a number, stripped version of numzi, or let's just call it a function. Okay, let's make a function called strip, which takes a number, right, and removes the even powers, removes the even powers of prime factors. Okay, even power prime factors. So it's only going to give us a value which is odd power prime factors, right? So if you do strip of 12, that will be equal to 3, right? Because we removed this is even, and we only left with 3. If we do strip of 27, then that's equal to 3 squared times 3, right? So we're going to just remove that 3 squared and we're just going to give a 3. So we'll be like 3, right? Now, since strip of 12 is equal to strip of 27, we know that if you multiply these 12 and 27 together, then they will form a perfect square. Okay, perfect square. So we're going to write in general, if the way we have defined strip, okay, using that definition, if strip of u equals strip of v, right, then u times v is a perfect square, okay. So let's use this in our example over here. What is strip of 10? Strip of 10, 10 is equal to 5 times true, right? And it's equal to 5 times 2, so that will still remain 5 times 2. Strip of 10 is equal to 10. So we're stripping off all the even factors of the primes. Strip of 27 is 3, strip of 3 will also be 3, and strip of 12 will also be 3, right? So basically that's why we saw that multiplying 12 with 3 or multiplying 12 with 27 is giving us a perfect square number, because the odd numbered prime factors in 12, we want those to also be odd numbered in the ancestor, and that's what we're basically doing with this strip function, right? We're finding only the odd number prime divisors. All right, so how do we use this to help us with our solution? So basically what we need to do is, for each node, so we get the idea, right? Idea for each node x, find strip of x, then count, or not strip of x, strips of num of x, right? Strip of nums x, then find all ancestors, then find the count of ancestors with the same value of strip, with the same value of strip of x. So ancestors will be y, so same value of strip of nums y, and we can do answer plus equal to the count, right? We want the sum of all these ancestor and child matching, so we can say answer plus equal to count. That's what we need to do for each node. Okay, so how do we do this? How do we find the count of the ancestors? Well, what we can say is, if you visit the nodes in a DFS order, okay, if you visit the nodes in a DFS order, visit nodes of a tree in DFS order, then when we're visiting a nodes of a tree in DFS, what happens is always the ancestors are processed before you, and they are the ones which are there in the process queue, basically, right? They are the ones which are there in the stack, basically, right? So when you're starting DFS, you go to some random site, you go here, and let's say you go here, and then you go here, right? And then once we come back from here, then we can go here, correct? And then we come back from here, we can go here. So every time when we're doing a DFS, the ancestors are on the stack, correct? That's the definition of DFS. Then we can go here, then we can go here, then from this we go here. Now we come back and we can go here now. So always in DFS, your ancestors are in the stack, right? Your ancestors are on this stack. So what we can say is, we will store the value of ancestors strip nums of I in a map while doing DFS. So when we reach a child, when we reach a node, we can simply do ans plus equal to map of strip of this number, right? So strip of nums of this node, right? So that's all we need to do For each node we need to do this. Then when we go through its children, we can basically say map of strip of this number plus plus nums x plus plus, go through its children, go to its children. Once we come back from its children, we need to remove it from the map, right? Because we need to process other things. So then once we come back from its children, we will just remove it, right? Once we're out of the stack, basically. So that's what we're doing, basically, like stack based DFS. And using our value of strip, we can easily count our answer, right? So let me just write the pseudocode neatly. Basically what we're saying is DFS, so answer is equal to 0, map is equal to empty. Okay, and we're saying so DFS, we're doing function, let's say DFS, and we have the node x, right? So what we can say is the first thing we have to update here is answer. So answer is plus equal to map of strip of nums of I, right? So when we just come in the node, we need to add the value of the ancestors which have the same value of strip of nums of I. Now we need to go to all its children in the tree using DFS. So we can say that map of strip of nums I plus plus, just so that when we come to the children of this node, right? When we come to the children of this node, for example, we're at this node right now, and when we go to its children, we know that this existed with this strip value, correct? Now for all adjacent nodes, for all adjacent unvisited nodes, those are my children, right? Or all adjacent nodes not equal to parent, all adjacent node, it's a tree, right? So all adjacent nodes not equal to my parent, we can do DFS for those nodes. So let's say DFS of y, and then when we come back up, when we have visited all the children and we're coming back up, we need to remove this from the map. So we can say remove the strip of nums of I from the map, right? And so that's it. We can use one DFS call and find the whole solution. Because we're using map, it is big O of n log n, and otherwise it would be big O of n. Although what about the strip function, right? The strip function, we need to remove all the divisors, right? We need to remove all the even factors, so we need to find all the divisors, right? So for the strip function, how to implement it? Find even divisors, even powered divisors, and remove them. So for this we need to find divisors. So the time complexity of this will be big O of root of the number, right? Big O of nums of I, correct? So let's just write down the full time complexity now. Time complexity, instead of map you can use hash map, and then the DFS will be big O of n, but I'm just using map because it's convenient. So the time complexity is big O of n log n plus the time taken to take strip of I, so that's square root of n. So it's big O of n log n plus square root of nums of I, right? And nums of I also goes up to 10 power 5 itself. So we can basically write this as big O of n log n plus root n, right? So this is the time complexity for the code. Memory complexity will be big O of n itself, right? Nothing extra memory is being used. Okay, so let's have a look at the code now. Here's the code. Here we are first implementing the strip function. So the stripped values are ans. For every divisor up to square root of v, we are finding all the divisors, right? Here we're maintaining a count of divisor. If it's even or odd, we remove the divisor and we do count plus plus. If the count was odd, then we can say that this answer gets multiplied, right? This divisor gets multiplied to the answer. If v is greater than 1, again we have a divisor, so we can do ans multiplied by v. So this is the strip function. Go through it. Pretty basic number theory. We're just finding the divisors. Okay, now we have our DFS function, right? Obviously it needs to take some inputs like the adjacency list, the map, the numbers themselves, and the answer. So these should be passed by reference. X is the current node, P is the parent node. Okay, so we find the stripped value, so I'm just storing the stripped value in advance itself. S is the stripped value of nums of X. Now I increase my count my answer by this much, the count of S, right? So the map of S, right, is the map, count is the name of the map. So I increase the answer by the count of the stripped value, count of the stripped value plus plus. For every adjacent node which is not my parent, I do DFS. Once I come back from the DFS, it basically means I'm removing from the stack. So I do count of S minus minus, right? So this DFS count gives us the answer. When we run the DFS, the answer gets stored in this variable, right? Now the body of the code, so main code, just make the adjacency list, make an empty map called count, make answer equal to 0, run the DFS, start at the root node with no parent, and finally once the DFS is done, we can just return the answer. So that's about it. Pretty simple DFS question in my opinion. Just some basic number theory you should be familiar with. This is the time complexity, right? And to be honest, today's contest was fairly easy, in my opinion. I'm not sure how it was for you guys. So yeah, that's about it. Thanks for watching everyone, and see you in the next PCD. Bye bye.